Okay, in this screencast we're going to concentrate on the difference between instantaneous and average. In this case we're going to concentrate on speed. So it's not vector versus scalar, it's not velocity versus speed, it is at this instant versus over an entire trip. So the instantaneous speed of an object is the speed at that particular given moment in time. Right now, not some kind of over a longer period of time. If you're looking for an average speed, your instantaneous speed can be very different, but we could average it over an entire trip. Now, whenever you're looking for the average speed is simply the total of the distance traveled, whether it be back and forth, up and down, whatever it is, it's the total distance divided by the total time. So it forms a ratio, a division of one by the other. Now, that doesn't matter if the speeds are changing. Doesn't matter if you travel at a high speed for a few minutes and a slow speed for another. You don't try to average by doing some kind of mathematical average or anything else. You take the total distance divided by the total time. Okay, we're going to look at a couple of cases. In the first one, we're talking about the data here on the chart. And we're talking about somebody driving their car along a highway. And they start at 0 time. We track their motion every minute, where they're located, and it takes them, in that time period, they go 7.6 miles. So the first thing we want to do is figure out the average speed in miles per minute. Now, again, average speed, that's V. To show it's an average, you might see a bar over the top, some kind of line over the top to indicate it's kind of an average over in a longer period of time. Is equal to the total change in distance divided by the total change in time. Again, the triangle is delta for change. In this case, they started at 0 and they went to 7.6. So their total change of distance was 7.6 miles. And their total change of time, we started at 0 time and it was 10 minutes. So that is 0.76, and the units are miles per minute. Not a common measurement, but in this case we could do that. We could also turn it into miles per hour and see what that is. Now in part B, we're not looking for the average over the entire part of the trip. We're looking for during what interval, during what time interval, gap between two different times, were they going the fastest. Now if you're going to look for that, keep in mind that speed is change of distance over change of time. All of our time intervals are going to be 1 minute. So what we need to look for in order to maximize the speed, we need to look for a place where the delta D, the change in distance, is a maximum. So let's see, 0, that's 0.4 in that interval, 0.4, 0.8 minus 0.4 is another 0.4, 0.5, 0.8, back to 0.4, 0.2, 1.1, 1.2, 1.4, and 1.2 again. So 1.4 is the biggest gap that we have between the 8th and the 9th minute. So that's 1.4 miles in that 1 minute time. Now if you convert that out, that's approximately 84 miles per hour. So during that 1 minute interval, the average was 84 miles per hour, which of course is beyond most speed limits. So maybe in the far west you could go that fast, but not around here. Okay, now a table is one way to look at data and try to parse out what is going on. Another good way, and actually even better way, is to have it in a graphical format. So here we have Donovan Bailey back in the 1996 Atlanta Olympics. He ran a record-breaking 100 meter, and here are the intervals every 10 meters of distance is marked out with the time it took him to at which he was at that point. So he started here at 0, and then 1.9 seconds later he was at 10 meters, and then at 3.1 seconds from the start he was at 20 meters. So we're looking for during what interval did he have his greatest average speed, and then we want to calculate that. Now, what you visually want to look for to speed this up a little bit, on a graph of distance versus time, the slope is equal to the speed. So the biggest speed is going to have the steepest, most upward slope. Since all the slopes in this case are upward, we want the one with the steepest climb. So if you peruse and look over these, you should notice that the one with the steepest climb is going to be the one that is in this gap from 40 to 50. That's a little bit steeper. This is a little more shallow. This is a little more shallow. That's the steepest section. Now, to determine his average speed, we simply need to know the distance that he traveled and the time that it took. Now, the distances are all 10 meters for every interval or gap. The time interval for this one is from 4.9 to 5.6. So that's 0.7 seconds. So 10 divided by 0.7 is going to give us 14.3 meters per second. Now, we can talk about the accuracy of that measurement, but for now, we're just interested in actually calculating it. That's a little over 14 meters per second during that one 10-meter section of the trip. 14 meters, that's a good long distance. It's certainly the width of the classroom. So this person is traveling that width in 0.7 seconds. Okay, now in this second part, we're looking for the average speed for the overall race. Again, anytime you're looking for the average speed, you're looking for the total change in distance divided by the total change in time. So it's a 100-meter race, so it's going to be 100 meters. And the time total is 9.84 seconds from start to finish. That's a 9, not a 7. And that gives us an average speed during that time period of 10.2 meters every second. Still impressive, over 10 meters every second of time, not quite as large as that interval in which he was able to make the maximum speed of about 14.3 meters per second on average. Okay, so using tables and graphs is a great way to try to track a motion that occurs over a time period. In certain situations, we're interested in the speed over a long period of time. Sometimes we want something at a moment or an instant in time. So average versus instantaneous.